So this is a review for test 3, which covers section 5.1 to 5.3 and 6.1 to 6.3. And actually 5.3 was how to find eigenvalues and eigenvectors, and you will find them as you solve things in chapter 6, but no questions directly from there. And then 6.1 was vocabulary and notation, and there's no questions directly from there, but you will find the vocabulary and notation in the other things from chapter 6. So really 5.1 and 2, that type homework questions, and 6.2 and 3. All right, so let's start by we need to be able to determine a vector space mapping and then also if a transformation is linear or not. So for the mapping, you look at the vector that's going to be transformed, and it has an x and a y, two components, so it's R2. Once transformed, it has two components again, so you're mapping to R2. Now to check to see if the transformation is linear, you have to check both scalar multiplication and addition and make sure they're closed. So that means if you did a transformation and you put a c in, multiplied the constant in first, and then applied the transformation. So let's do that. So to transform, you take 2 times whatever was the x. And then for the second component, you multiply the x and y ones together. That's c squared x y. Now, if we did the c later, so in other words, we went to do the transformation and we transform x and y and then multiply it by c. So here's the c. Let's transform x and y. So that's going to be 2x and xy. Now multiply the c through, and that's going to be 2cx and cxy. Now when we compare these two, this one has a c squared and this one only has a c, so they are not equal, so this transformation is not linear. Now to determine if a transformation is injective or surjective, remember injective is 1 to 1 and surjective is onto, meaning it has a preimage for the whole space, so the whole space gets hit by something that's transformed. So if we check the 1 to 1, one of the easiest ways to do this is to check what we now know is called the kernel. Check what maps to the 0 vector. If only 0 maps to 0, 0, then it will be 1 to 1. But if there's more things that map to the 0 vector, then it's not 1 to 1. So let's look at this and see what would map to 0, 0. Well, in the preimage, if we had 0, then 2x would be 0, but y could be anything because you're going to be timesing it by x, which is 0. So the kernel are all of these vectors that have 0 for the x and anything for the y. So the kernel is not just the 0 vector, so this is not injective. Now surjective, we want it to see if when we're mapping this from R2 by taking these xy vectors and we map them over here to 2x and xy, does everything that lives over here in R2 have a preimage, so means something over here went over and mapped to that. So we need to look and see if anything that we get in the image, if we could always get a pre-image. So let's just do a couple examples. Let's just say we had anything in R2. So let's have 1 and -7. Well, is there a pre-image that would get mapped to that by this transformation? Well, this would have been 1/2. And that way when we do 2x we get 1, and then we need to just pick b, so when we multiply it by a half we get -7, so -14 would do that. So when we multiply these together we get -7. And you can see that whatever I picked then, if I did half of it here for the a, and then if I did 2 times it here for the b, then those, when we transform them, would map to this 2x and xy. So it is onto. So it is not injective, but it is surjective. Okay, let's look at another one here. I've got 2 component vectors, so I'm mapping from R2. Once I get it mapped, it has 3 components, so I'm mapping to R3. So we're going to first check that if I put a c in there, multiply through by a scalar multiple, and I transform it, then that would be 2 or cx and then 2, and then cy. And so now what if I did the c in a minute and I transform the xy and then multiply the c through? So if I do that, I have c times transforming x, so it'd just be x, 2, and y. And so when I multiply that through, I get cx, 2c, and cy. And you can see that the middles don't match, not equal, so this is not linear. All right, let's look at one more. Transforming three component vectors. So in R3, when I get them transformed, they have three components, so mapping to R3. All right, so we're going to first of all check that if we transform with a cx in there, so that'd be a cy and a cz, if we apply this transformation, we'll get 0 and whatever was in the x, which is cx, and then whatever is in the y, which is cy. Now what if we instead do the c later and we transform x, y, z and then multiply the c? So here's the c out in front, transform it, 0, x, and y, and now distribute the c through. So we have 0, cx, and cy, and we see that those match. So the first property of linear transformations hold, the scalar multiplication. Now we have to check the addition. So we're going to take two vectors, u, which is u1, u2, and u3, and v, which is v1, v2, and v3, and we're going to take and we're going to add those together. So we add components. u1 plus v1 is the first component, u2 plus v2 is the second, and u3 plus v3 is the third. And now we transform that. So we have 0, and then the x, which is u1 plus v1, and then the y, which is u2 plus v2. Now what if we instead transformed u and transformed v, and after the transformations add them together? So transforming u, we would have 0, and then u1, and then u2, and then we'll have plus. Transforming v, we'd have 0, and then v1 and v2. We add them component wise. This one plus this one will give us 0, and the second component is going to be u1 plus v1, and the third one's going to be u2 plus v2. Now when we compare that to when we added first or added later, those match. So both properties hold, so this one is linear. All right. Now this one, if we have a linear transformation, we should be able to come up with a matrix for it if it's a linear transformation. So we're looking here, and this is what it transposes to or transforms to. So let's just go ahead and make a matrix A, so that if we were to multiply it by x1, x2, and x3, we would get exactly this. So there must be 2 on here and -1 for the x2, and there's a comma there, so the whole first component is just this much, so this one must be 0. And then the middle component is just x3, so this needs to be 0, 0, and 1. And then the last one, we have -1 on the x1, 4 on the x2, and 3 on the x3. So if I multiplied this matrix by this column vector of the different components, then I would end up with this. So there's our matrix A. Okay, so let's take this matrix A and transform, and we want to find the kernel, the image, the nullity, and the rank, and a geometric description, and then we'll talk about the rank nullity theorem. All right, so if I was to multiply across the row and down this column vector, it would need to have the same amount. So this is going to have an x1, an x2, and an x3, since there's 3 columns. As I go across that row, there's 1, 2, 3 things to multiply. So I'm starting in R3, And when I multiply them, I'm going to go across the first row and down the column and get one answer, and then across the second row and down the column and get a second one. So I'm going to have a 2-component vector, something in R2, when I do the multiplication. So now we're going to find the kernel and the image, and the way to do that is to start with the matrix A and get it in RREF, and then we will find the different things we need. So first thing, I'm going to keep the first row, and then I'm going to do 3 times row 1 plus row 2. So that would be 3 minus 3 is 0, 3 times that's negative 3, plus 3 is 0, 3 times that 6, plus 6 is 12. Okay, then I'm going to do 1/12 row 2. So that's going to be 1, negative 1, 2, and 0, 0, 1. Then I'm going to use this one to zero out the 2 above it. So I'm going to do row 1 minus 2 row 2, and that would be 1, negative 1, 0, and 0, 0, 1. So this is the RREF of A. We can tell a couple of things from this. We can figure out what the kernel is then, because we could augment this with zeros, put the variables back in, and that what we have would build the kernel. So let's just use x, y, and z for our variables here. So first of all, x and z are our bound variables and y is free. Z equals 0. That's just simply in this second equation putting the variables back in the equal sign. Z is 0. Y is free to be whatever. And so x is going to be minus y equals 0. So if we move that over, that would be, since y equals t, a t. So I'm going to factor the t out and have 1, 1, 0. And so this is the kernel. So kernel of the transformation is built with a vector 1, 1, 0 and any scalar multiple of that. So the kernel, geometric description wise, it's built with one vector, so it is a line in R3. And it's R3 because there's 3 component vectors. Now we're going to find let's go ahead and answer the nullity. The nullity is the dimension of the kernel. It's built with one vector, so the nullity is 1. Now let's see about finding the image. When you get the matrix in RREF, the leading ones, the columns they are in, those are the pivot columns. You go back and find the original columns in the matrix that correspond to those columns that had the leading ones, and that's how you build the image. So the image of this transformation is it's the span of the vectors 1, negative 3, and 2, 6. So the rank is the dimension of the image, and the image is built with 2 vectors, so its rank is 2. The rank nullity theorem says if you add the rank, which is 2, plus the nullity, which is 1, it will equal the dimension of the original space, and the dimension of the original space was 3. So there's the rank nullity theorem, and it does check out because 2 plus 1 there equals 3. Geometric description of the image. The image, we have 2 vectors to build with, and we're building in R2, and so the geometric description is it's all of R2 because it's built with 2 vectors in a 2-dimensional space. Okay, we want to find the kernel of this transformation that maps from functions with 2 continuous derivatives to continuous functions by taking 2 derivatives. This is the mapping right there. Kernel is what maps to 0, so it would be when this differential equation equals 0. So when you're talking differential equations, another way to express the kernel would say the solution to the homogeneous differential equation. All right, this is r squared plus r equals 0. Factor out an r, that leaves r plus 1. So we have our 2 roots. Our roots are going to be 0 and negative 1. So remember, we build our solutions by taking our function. So I'll just put f of x or f of t, doesn't matter. Okay, so this is going to be C1 e to the root 1t plus C2 e to the root 2t. Now just to simplify a little bit, e to the 0 is 1, so this is just going to be C1 plus C2 e to the negative t. That is the kernel of this transformation. It's also the solution to the homogeneous equation. Okay, let's go ahead and look at the next one. We need to find the general solution. This is a matrix vector form of a system of equations, and then sketch the eigenvectors with their flow and a couple of typical solution curves. So we're going to start by doing 1 minus lambda. Down the main diagonal we have the minus lambda, so this is a minus lambda i's determinant. That gives us a lambda squared minus 3 lambda minus 1, so minus 4 lambda, and then 3 minus 8, which is minus 5, equals 0. So there's our characteristic equation. So let's go ahead and factor that. That's going to be lambda and lambda minus 5 plus 1 equals 0. So lambda 1 equals 5 and lambda 2 equals negative 1. So now we're going to find the corresponding eigenvectors. So first with 5, we take a minus lambda I, which was right here, and we put in 5 for the lambda. So 1 minus 5 is minus 4, then we have a 4, then we have a 2, 3 minus 5 is minus 2. So we're figuring out the eigenvectors, so when it equals 0, you can see there's a dependency there, but really for 2 by 2's we don't have to do any row operations because we know the second one's going to 0 out. So let's just work with the first row there, put the variables back in, negative 4v1 plus 4v2 equals 0. So we can take the 4v2 and move the v1 to the other side. We can reduce by 4's, so the eigenvector is going to be any vector where v1 equals v2. We'll go for the easiest one then. We'll make them both 1's. Now let's go ahead and take the second eigenvalue, which is negative 1. We put it back in this a minus lambda I matrix. 1 minus a minus 1 makes a plus 1, so 1 plus 1 is going to be 2. And then we've got 4, and the bottom row is 2 and 3. Minus minus makes a plus, that'll make that 4. You can see the dependency there. Let's go ahead and just put the variables back in. 2v1 plus 4v2 equals 0. So 4v2 equals negative 2v1. And so 2v2 equals v1, negative there. All right, so an eigenvector for that one. Let's go ahead and let v be negative, v2 be negative 1. That way if I put a negative 1 in right here, then we see that v1, the negatives cancel, and v1 must be 2. So there's our corresponding eigenvectors, and now we build the solution. The solution will be a linear combination, c e1 to the eigenvalue t multiplied by its eigenvector, plus c2 e to the eigenvalue t multiplied by its eigenvector. So there is our solution to the system. Now, besides the solution, we're supposed to sketch the eigenvectors and put their flow to get a couple of curves. So I don't have a ton of room. I'll put it just down here. So here's our grid. Let's first of all plot the eigenvector 1, 1. So over 1 and up 1, and scalar multiples would be right here. The corresponding eigenvalue is 5. That's positive. That would make an e to the 5t, and over time that's going to go to infinity. So we're going to draw the arrows going away from the origin, going out. If you start out with like e to the 5t, it's going to go to infinity. If you start out with negative, a negative coefficient, and then e to the 5t, that's going to go to negative infinity. All right, second eigenvector right here. Let's plot that. We go over 2 and down 1. So it's going to look like this. And the corresponding eigenvalue is negative 1. E to the negatives approach 0. So these arrows are going to go in. There is an equilibrium solution right there at the origin. However, it's unstable because typical solutions are going to come in and then end up heading out. They're going to kind of try and come in, but then the e to the 4t will dominate and they end up heading away. All right, let's look at the next one. We need to be able to convert a second order system to a system of first order equations, and then we also want to be able to solve it. So you do a change of variables. You call x1 y, whatever our variable was here, and that means x1 prime is y prime. Then we also need x2, and that's going to equal that y prime, so that x2 prime is y double prime. So by the time we get our system, we don't want a second derivative in there, so we do the substituting. And what we want is we want a system that has x1 prime equals something and x2 prime equals something. First order system in this matrix vector form. All right, so x1 prime was y prime, but that was x2, so we can fill that in. Just looking at that'll always be the case when we do this substitution. But x2 prime is going to come from subbing these x variables in the differential equation and solving for x2 prime. So y double prime is x2 prime plus y prime is x2 minus 12y, and y was x1 equals 0. So now we're going to solve this for x2 prime by moving the other two to the other side. I'm going to write the x1 one first when I move it over, and then the x2 one, because when I put it in the system I want it in order, so when I write down this matrix I can easily see and have it in the right order. So we could now solve this system of equations using the eigenvalues and eigenvectors, and that's what we're going to do. Okay, so let's express this system of equations that we came up with in matrix vector form. It's going to be an x vector prime equals, our A is going to be 0, 1, 12, and -1, and then x. So now we can solve that by first finding eigenvalues and eigenvectors. So we're going to take a minus lambda I, so it's going to be 0 minus lambda, 1, 12, and -1 minus lambda. Let's compute that determinant. I'm going to get lambda squared, and this is going to be plus lambda, and then I've got minus 12 equals 0. So this will factor, and it'll factor into, let's see, I've got 4 and 3, and this will be plus and this will be minus. Okay, so I've got two eigenvalues. The first one of those is going to be -4, and the second one is going to be 3. So let's go find an eigenvector to go with -4. So we take back up here where our a minus lambda I is, and we put in -4. Well, negative of -4 is 4, 1, 12, and -1 minus a minus makes a plus 4, so that makes that 3. Okay, let's go ahead then, and we can see the dependency there because the second row is 3 times the first row. So let's put our variables back in. 4v1 plus v2 equals 0. So we can move the v2 over, minus v2. So eigenvector, let's let v2 be -4, and that means if we put a -4 in for v2, that we would have 4, v1 equals 4, so v1 must be 1. All right, our second eigenvalue is 3, so let's do our a minus lambda I. That's going to make that a -3, and a 1, and a 12, and a -1 minus 3 is -4. You can see the dependency. -4 times the first row gives us the second row. Let's put our variables back in. -3 v1 plus v2 equals 0. So v2 equals 3 v1. So let's let v2 be 3, and that means v1 is going to be 1. Now we're going to build our solution, linear combination, c1e to the first eigenvalue t multiplied by first eigenvector plus c2e to the second eigenvalue t multiplied by the second eigenvector. So there is our general solution. All right, we are also asked to sketch the eigenvectors and show the flow. So let's go ahead and first we'll do the eigenvector 1, -4. So we go over 1 and down 4. And then scalar multiples would be a line here. Let's try and make it a little straighter. The eigenvalue that corresponds to this is negative. So e to the negative something will go to 0. So let's go ahead and put this approaching 0. And then let's go ahead and get the second one. The second one is 1, 3, so over 1 and up 3, and scalar multiples. The eigenvalue that corresponds to that is positive. E to the positive t is going to go to infinity, or negative infinity if it's got a negative on the front of there. So that's going to head out. So we have an equilibrium solution at 0, 0, but it is unstable because the flow is going to come in, but ultimately they're going to head out because the e to the 4t will dominate. So curves could look something kind of like that. So unstable equilibrium. So here we want to find the general solution for this system that has this as the matrix A. So first we're going to do 6 minus lambda, minus 1, 5, and 2 minus lambda. And multiplying, finding the determinant, lambda squared minus 2 lambda minus 6 lambda, which is minus 8 lambda, and 12 minus a minus makes a plus 5, so plus 17 equals 0. Okay, that won't factor, so we're going to quadratic formula negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. All right, so if we multiply here, we have 8, 68, so 64 minus 68, which is negative 4, which is plus or minus on that 2i. So we have 8 plus or minus 2i over 2, and we can reduce that to 4 plus or minus I. So those are our two eigenvalues. So we need to find an eigenvector. We're going to have it correspond to the 4 plus I. So let's put that in our a minus lambda I. So we have 6 minus 4, which is 2, minus I. And then negative 1 and 5, negative 2, and then minus I. Okay, so we're going to just take this first row and we're going to put the variables back in. This will be v1 minus v2 equals 0. So 2 minus I v1 equals v2. So our eigenvector, let's let v2 be 2 minus I, what was sitting in front of this, because then if we put that in there, we'll have the 2 minus I v1 equals 2 minus I, so v1 must be 1. So our eigenvector is going to be 1 and 2 minus I. Now we'll want to express that split up. So, I'm going to be off the screen if I do it right there. I'll put it down below. So it's going to be 1 and 2, and then plus 0 and negative 1. So those are going to be useful. We're ready to build our solution then. And the solution is going to be, we put them in a linear combination. We're going to have C1 e to the, this was a 4, so 4t, and then this is going to be on our real part, so that's going to be multiplied by, we're going to have cosine of, in front of it was a 1, so just cosine t times the real part of the eigenvector, minus because we had an I and an I for I squared, so that's going to be sine t times the imaginary part of the eigenvector. And then we're also going to have plus c2 e to the 4t, and we will have, comes from the imaginary piece, so that was going to be sine t times the real part of the eigenvector plus cosine t times the imaginary part of the eigenvector. So here is our solution. And we know when they have e to the something t's and cosines and sines, they want to go around circularly, but here the amplitude is going to be increasing, and so these guys from here are going to be spiraling out. You could do a couple different ones that came out, and that is going to be unstable. Okay, let's look at our last one, which is modeling problem with two tanks. So mixing problem here, we have two tanks and they each contain 200 gallons. I'll just kind of list that on there. So they each contain 200 gallons of water. Initially there's 100 pounds in tank 1 and 200 pounds in tank 2. So tank 1 at time 0, the amount of salt in it is 100, and tank 2 at time 0, the amount of salt in it is 200 pounds of fertilizer. Okay, I said salt, this one's fertilizer. Okay, so the inflow, circulation, and outflow are shown in this picture, and it's kept uniform by stirring. And so we want to we're not going to solve it, we're just going to set it up. It'll just ask you to set up the problem. So we're going to set up how things are changing. So we're going to have the rate of change in tank 1 is going to be rate in, concentration in, anything that's coming in, and then minus rate out, concentration out. So what's going into tank 1, as I'm looking here, I have rate in is 12 gallons per minute, and the concentration in it's pure water, so it has no fertilizer in it, so that's 0. Okay, we also have this one coming into tank 1, so plus rate in is 4 gallons per minute, and the concentration in will be the amount of salt in tank 2 divided by its volume. All right, now let's see what's going out of tank 1, and this is the only thing going out of tank 1, so that's a subtraction term. Rate out is 16 gallons per minute, and the concentration out is going to be T1 over 200. Okay, so now we have, that's for tank 1. Now we're going to have the rate of change of fertilizer in tank 2. So we're looking from tank 2 and saying what's coming in. 16 gallons per minute is coming in, and the concentration is the amount in tank 1 divided by its volume. And that's the only thing coming in. There's two things going out, so let's do this one at the top here first. So flow rate out is 4 gallons per minute. Concentration would be whatever's in tank 2 divided by its volume. And then we've got one more going out over this 12, and then the concentration there would be tank 2 over 200. So here is my initial value problem that models what's going on with the tanks.